Hello everyone, this is Dr. Lennon, and we're going to be talking about trig functions of any angle in this section. So previously we had discussed how to define a trigonometric ratio on the unit circle, or on right triangles, but that would only allow us to define trig functions basically for angles between 0 degrees and 90 degrees. But we want to talk about how to do that more generally, and in doing that, generally the radian is the preferred measure of talking about the measurement of an angle. So why don't we start right there defining what a radian is. You may know what this is already in terms of a conversion factor, but I'd like to pose it in terms of kind of a more geometric definition. So the definition here, let's say, given a circle of radius r, one radian is defined to be the angle, or the central angle, that subtends an arc on the circle of length 1 radius. So basically, if you take any circle and you have the radius, and imagine you took something that was kind of stretchy, that was like a elastic, like a rubber band, let's say, and you measured it out the same exact length as this radius, but then you stretched it around the circle to kind of get this outside shape here, then this angle that you would form by connecting the two ends of that on the arc, this angle theta would have measure 1 radian. So, the reason that it makes sense to do it in terms of radians is we know for every circle, the circumference formula, one whole circle has 2 pi copies of the radius there. 2 pi r is the circumference of a circle. So 2 pi radians has to equal 180 degrees. If we divide by the factor of 2 there, the conversion factor between degrees and radians is given by 180 degrees equals pi radians. So I'll use RAD here for the way to determine the unit radian. Oftentimes when the context is clear, that's not written. But since we're just introducing it, I'll try to write RAD anytime I mean radian rather than degree. And because this is determined or is defined purely in terms of arc lengths, we have this very nice formula for the arc length of a circle that I'll mention. The arc length formula is, so this is a cursive S here that stands for the arc length, is equal to r times theta. And it's only valid if theta is given in radian measure. So if you want to apply that formula, you can't have, say, a circle of radius 2 inches and a degree of 30 and an angle of 30 degrees and say, okay, well, 2 times 30, it's got to have a arc length of, what would that be? 2 times 30, 60 inches. That wouldn't make any sense. So if you want to use that formula, you first would have to convert your degrees to radians using the above conversion factor. Then you could apply the arc length formula. Okay, so let's talk about the unit circle. So the unit circle is basically what we use to extend the definition of the trig functions here. So the unit circle is the circle of radius 1 centered at the origin. So in Cartesian coordinates, the curve can be described by the equation x squared plus y squared equals 1. So basically, let's just start by defining sine and cosine. So we define the sine and cosine of an angle theta. So theta is kind of like our generic angle that we use. So that's just the lowercase theta from the Greek alphabet. So starting at the positive branch of the x-axis, measured counterclockwise, as coordinates on the unit circle that intersect the angle. So it'll be much more clear once we draw a picture here, but we're just writing it down in words first. So let's draw a circle. So if we draw some circle, there's probably a way with this one note that I could do it perfectly, but I'm not exactly sure how to do that. So let's say this is so let me draw as a dotted line. Let's call that the y-axis, and then horizontally this would be the x-axis. So this is our radius right here. So if we have some point on the circle, then this angle theta is measured counterclockwise from that positive branch. So that's the x-axis that I have as the shaded line right here. That's that part of the x-axis. That's what I'm talking about. The positive branch of the x-axis is the part that is to the right of the y-axis. So we start from that part and then we measure counterclockwise until we intersect that point that we're discussing. So the xy coordinates that represent this point right here on the unit circle corresponding to that angle theta are the cosine of theta and the sine of theta respectively. So on this unit circle measurement, the cosine is representing the x coordinate and the sine is representing the y coordinate. And you can kind of see the way that we can understand where the right triangles are coming from is if you look at another picture with the same kind of point. So if you have the same type of triangle that we're talking about, where the right triangle comes in is if you drop a perpendicular, so a line parallel to the y-axis until it intersects that positive branch of the x-axis, in this case, we get a right triangle. Now, that's how the right triangle is kind of associated to this unit circle. However, we're going to be more flexible on this unit circle because we can talk about any angle. We don't have to stay in quadrant 1. We could also move that point to quadrant 2 or quadrant 3 or 4, and then or even multiple rotations of the circle. And in that way, we can talk about the sine or cosine of any angle. So let's review from geometry, two important right triangles, so that we have some examples to work with as we move along the unit circle and then go from there. So let's recall from geometry. Two important right triangles. So these are important in the sense that we can completely characterize the relationship between the lengths of the sides of these right triangles. So the first triangle we're talking about is the 45, 45, 90 degree triangle. So this is the only isosceles triangle, meaning two of the sides have the same measurement. So if you have a 45, 45, 90 triangle, that's talking about what the two angle measurements are. So we have 45 here and 45 here. And the way the relationship between the sides work is the hypotenuse, if that has measurement 2a, where a is basically just some constant multiplier, then the other ones can be determined. The legs are going to have lengths a radical 2 and a radical 2. Because this triangle is isosceles, meaning two of the angles are the same, then two of the sides will also have the same length. So on a unit circle, what is the value of a? Well, on the unit circle, the hypotenuse is always going to be 1. That's going to be the radius. And on the unit circle, the radius is 1. So that would mean a is equal to 1/2. So let's see what this triangle looks like on the unit circle. So on the unit circle, let's say r equals 1, so a must equal 1/2. Well, that gives us this triangle right here. So our 45, 45, 90 triangle will have side lengths of 1, 1/2 times the square root of 2, or the square root of 2 over 2, and the square root of 2 over 2. So those are our three sides. So what is the other important triangle? Other important right triangle that we typically learn about in geometry? It is the 30, 60, 90 right triangle. I have some loose. All right, sorry. Okay, so the second right triangle is the 30, 60, 90 right triangle. Again, we have a nice relationship between the lengths of the sides there. So this one, if we draw something approximating the 30, 60, 90, what is the relationship between the sides? Okay, so this is the smaller angle 30, this is the larger 60, and this angle here is 90. So the relationship between the sides, the hypotenuse should be 2a. The long side that 60 opens to is a radical 3, and the one that 30 opens to is a radical 2. So again, on the unit circle, we have the same deal. R is equal to 1, so a has to be 1/2. So on this unit circle, this will look like we'll have 1 as the hypotenuse, which makes the short side 1/2, and the longer of the two sides the square root of 3 over 2. Okay, so this will allow us to basically determine the sine and cosine of any angle that's a multiple of 30 or 45 degrees in the unit circle. So let's see how we can do that. And also let's note, since we talked about radian measure, so note that 30 degrees is equal to pi over 6 in terms of radians, and 45 degrees is equal to pi over 4 in terms of radians. To check that, if you don't know how, we just use the unit conversion factor. So take 30 degrees and multiply by pi over 180 and simplify, and the same for 45 degrees. Multiply by pi and 180, pi divided by 180, and you'll get pi over 6. So again, let's think about the sine. So we'll do this in two parts. First, we'll think about doing it as the multiples of 45 degrees. Then we'll do it as the multiples of 30 degrees. So the multiples, or let's think about the sine and cosine of all multiples of 45 degrees. Which we know to be in radians pi over 4. Okay, so how do we do this? Well, how many, let's count by 45 degrees starting at 0 degrees. So 0 degrees is right here. Let's think about all the possible angles we have. So if we split the circle into 4 pieces, each one of those is 90 degrees. And then if we subdivide in half, each one of those will be a multiple of 45 degrees. So this is 0 degrees or 0 radians, either way. And then we have 45 degrees, which is pi over 4 radians. And then we have 90 degrees, which is pi over 2 radians. And 135 degrees, which is 3 pi over 4 radians. Then we have 180 degrees, which is pi radians. We have 225 degrees, which is 5 pi over 4 radians. We have 270 degrees, which is 3 pi over 2 radians. And then we have 315 degrees, which is 7 pi over 4 radians. And for angles that are bigger than those, you just keep going around the circle in the counterclockwise direction. So our goal is to figure out, basically we want to fill out this chart. Theta, cosine of theta, and the sine of theta. And the reason I'm listing cosine first, again, because cosine is representing the x-coordinate of any of these points we're looking at on the unit circle. So, okay. If I want to figure out cosine and sine of 0 degrees, which in terms of right triangles doesn't even really make sense to us, because you can't draw a triangle where one of the angles has measure 0 degrees. It's not possible to do. But in terms of this unit circle definition, it makes some sense, right? 0 degrees, where it intersects the unit circle is right here. We just have to think, what are the coordinates of this point? Well, the coordinates of this point are 1 for x and 0 for y. So that means if we look at the cosine of that angle, it's got to be the x-coordinate, which is 1, and the sine of that angle has to be the y-coordinate, which is 0. So then what would we do? We would go to the next point. So we want to figure out what are the coordinates of this point at 45 degrees. Well, if we form the right triangle that we talked about doing, so basically we've got the right triangle by dropping the vertical line parallel to the y-axis, we get this triangle. So this triangle looks like one of these 45, 45, 90 triangles, and the x-coordinate is going to be the length of the horizontal side, which should be square root of 2 over 2, and the y-coordinate should be the length of the vertical side, which is also square root of 2 over 2. So that is what allows us to determine the sine and cosine of that angle. So we end up with square root of 2 over 2 and square root of 2 over 2. So then we can move to the next one, 90 degrees. And 90 degrees, we need to figure out the coordinates of this point. Well, the coordinates of this point are, so we can't form a triangle again because you can't have, if you drop the vertical line, it's going to be right on top, so you're not going to get a triangle, but we can determine the coordinates of that point. The coordinates of that point are 0, 1. So in this case, at 90 degrees, the x-coordinate is 0 and the y-coordinate is 1. So for 90 degrees, the cosine is 0 and the sine is 1. And now let's go ahead and move to the next one, 135 degrees. So for 135 degrees, we're going to get a similar looking triangle to the one we did above, right? We're going to move over here to this point, and then when you drop the perpendicular to the x-axis that's parallel to the y-axis, we get a 45, 45, 90 triangle again. And again, we're going to get square root of 2 over 2 for both of the side lengths. But now the question is, so the question that remains kind of is, so this was for 45 degrees, and this is for 135 degrees. So the question is, what are the sines, SIG and S, of the coordinates in quadrant 2? So in quadrant 2, we know that we have to have, so if you look at any xy pair in quadrant 2, we know that the x coordinate must be negative because it's left of the y-axis, and the y coordinate must be positive because it's above the x-axis. So the cosine is not just going to be square root of 2 over 2 for 135, it's going to be negative square root 2 over 2. And the sine will be positive square root 2 over 2. And then as we move to 180 degrees, again, that's another one where we just figure out the ones that are either on the x-axis or on the y-axis. We're just kind of determining what the coordinates of that point are, and in doing so, we actually figure out the sine and the cosine. So here, the coordinates of this point are going to be -1 for x and 0 for y. So for 180 degrees, we get -1 for the cosine of theta and 0 for the sine of theta. And you can continue with the unit circle. So I would continue to, I would ask you to continue thinking about what those values should be for quadrants 3 and quadrants 4. You should be able to use the same idea. All of these triangles are going to be 45, 45, 90, and you also have 2 other points on the x and y axis to think about. But that's all you're doing is replacing sine and cosine by square root of 2 over 2 for the triangles that are 45, 45, 90, and then you're thinking about what are the sines of x and y in their respective quadrants. And that's all you're doing to figure out the sine and cosine. So we're combining this fact from geometry along with our understanding of the coordinates from the Cartesian plane. Okay, so how about if we move to multiples of 30 degrees? So let's go ahead and do that. So let's, I did that already. I wrote down the multiples in terms of radian measure as well. So let's do the multiples of 30 degrees, which will be the same thing as pi over 6 radians. So because this special triangle from geometry has 2 different length sides, we're going to have a lot more places on the unit circle to determine angles. So, okay, so let's draw our unit circle again, which doesn't look so much like a circle, but you get the idea. So we have this spot, and again, all the multiples of 90 will also be multiples of 30, so we can kind of subdivide the unit circle into 4 pieces, and then each of those pieces we kind of subdivide into 3. So we have 30 degrees here, and then we have 60 degrees, and then we're just dividing each of these fourths into thirds. Probably there's some tool that would make this more accessible, but I don't know how to do it off the cuff. All right, so in terms of these angles, again, we have 0 degrees and 0 radians here. And then we have 30 degrees, which is pi over 6 radians. And then 60 degrees, which is pi over 3 radians. Again, you can kind of think about it as when you're counting the radians just by counting by multiples of 1/6 and then sticking a pi on top. So 1/3 plus, or 1/6 plus 1/6 makes 1/3. So that's why 30 degrees plus 30 degrees is 60, and pi over 6 plus pi over 6 is pi over 3. On top we get 90 degrees, which is pi over 2, which would be the same as 3 over 6 with a pi. And then we have 120 degrees, which is going to be 2 pi over 3. We have 150 degrees, which is 5 pi over 6. We have 180 degrees, which is still just pi. We have 210 degrees, which is 7 pi over 6. We have 240 degrees, which is 4 pi over 3. We have 270 degrees, which is 3 pi over 2. We have 300 degrees, which is 5 pi over 3. And we have 330 degrees, which is 11 pi over 6. Okay, so those are all the angles we care about. So on the multiples of 90 degrees, again, those are all found just by using the coordinates of the that are on the x and y axis. So again, if you look at the coordinates of each of these, at 0 degrees, the coordinates of your point intersecting the circle would be 1, 0. At 90 degrees, the coordinates of your point intersecting the circle would be 0, 1. At 180 degrees, it would be -1, 0. And at 270 degrees, it would be 0, -1. So that takes care of those points. But the other points, let me basically let's just look at the first two when we're looking at 30 degrees and 60 degrees. So at 30 degrees, when we have our triangle, it's the one that's closer to the x-axis. So it's kind of this shorter triangle like this. So our 30, 60, 90, where is the 30 degree angle? Well, the 30 degree angle is here, and the 60 degree angle is up here. So that makes our x-coordinate the longer of the two coordinates, which is going to be the square root of 3 over 2, whereas the y-coordinate is, so that's the length of this horizontal side, and the vertical side is going to be shorter, which is 1/2. So the coordinates of this point right here at the 30 degree angle are going to be square root of 3 over 2, comma 1/2. And when you do it for 60 degrees, the y-coordinate is going to be the bigger of the two. So when we have the 60 degree angle, and you look at the unit circle again, we're going to be up here. So when you drop the perpendicular to create your 30, 60, 90 triangle now, it looks more like this. So we've got a longer y-coordinate and a shorter x-coordinate. So for this one, this is now my 60 degree angle, and this is my 30 degree angle. So this side is 1/2, and this side up here is square root of 3 over 2. So that makes the coordinates of this point, this time, 1/2 for x and square root of 3 over 2 for y. So if we think about making the same sort of table where we're looking at theta, cosine of theta, and sine of theta, and we'll do at least the first two quadrants like we did for the multiples of 45 degrees. We have, so again, starting at 0, if we want to include that, the cosine is 1, the sine is 0. So now the first interesting one is 30 degrees. So that's the one we just did below. So the cosine was the longer side, square root of 3 over 2, and the sine was the shorter at 1/2. 60 degrees, they just reversed. We had 1/2 for the cosine and square root of 3 over 2 for the sine. 90 degrees is right at the top, so the cosine of 90 degrees is 0, and the sine of 90 degrees is 1. So now we want to do 120 degrees and then 150 degrees. So they're going to be similar in nature to the 30 and 60 we just looked at, but they are going to be in quadrant 2. So in quadrant 2, what's going on? Well, so let's do 120 degrees. I'm sorry. 120 degrees, and then 150 degrees. So 120 degrees is going to be the taller right triangle, meaning it has a bigger y coordinate or y component side than x component side. So it looks something like this, where we have our 60-degree angle here and our 30-degree angle here. So our y side should be the longer of the two, which is square root of 3 over 2, and the x side will be shorter at 1/2. What are the coordinates? Well, we're in quadrant 2, so in quadrant 2, my x has to be negative. So I'm going to have negative 1/2, the horizontal value, and the vertical side will be square root of 3 over 2. And for 150, I'm going to get something, the triangle is going to look more like the 30-degree case, because it's going to have the shorter y component side and the longer x component side. So now my triangle looks like this. So I've got 30 here and 60 here. So now my vertical component is 1/2, and my horizontal component is square root of 3 over 2. And then, as before, to figuring out the components, we just apply the sign to the appropriate one. So in this case, the x coordinate of this point is going to be negative. So for this one, we have negative square root 3 over 2, comma 1/2. So that's how we figure out the sine and cosine of those values. So let's fill those in. For 120 degrees, the cosine was negative 1/2, and the sine was square root 3 over 2. And for the cosine of 150 degrees, we had the longer x component, negative square root 3 over 2, and the shorter 1/2. So that's quadrants 1 and 2, so I encourage you to try and finish quadrants 3 and 4. Again, this is just the case for our special triangles. So for other angles, we typically just appeal to a calculator. But our geometric thinking does not change. So what does that mean? Well, let's say let's say, example. So let's find the coordinates of the point, or the given point. So let's say we have a unit circle, and maybe we have some point that's not given by a multiple of 30 or 45. Maybe it's not so nice. So let's say, I don't know, we have some point like this, and we're told this angle has measurement 250 degrees. Okay, so basically, if this point has coordinates x, y, we know x is just going to be the cosine of 250 degrees, and y is going to be the sine of 250 degrees. Now, a lot of times if we're using this to make some sort of measurement, we want to know some decimal approximate value. Often these things are going to be irrational numbers, meaning their decimal expansions neither terminate nor end. So usually we'll have to have some degree of accuracy that we want. Let's say we just want to approximate to 2 decimal places here. So we always want to make sure that our calculator is in the appropriate mode. So here we want to be in degree mode, not radian mode. So let's type in the cosine of 250, we get negative 0.34. And if we do the sine of 250, we get negative 0.94. Is it good that they're both negative? It sure is, because we know 250 degrees is between 180 degrees and 270 degrees, which puts it in quadrant 3. So in quadrant 3, our x and y should both have a negative value. So that makes sense here. Okay, so just a couple other things to say about our trig functions. So in general, for the right triangle, we said the sine was opposite over hypotenuse. Cosine was the adjacent over the hypotenuse, and the tangent was the opposite over the adjacent. Well, if you notice, if you look at, so what did we say? We said sine of theta was opposite over the hypotenuse, cosine. So in right triangle, so this is the end of the example. So in right triangle, trig, we had these definitions, the adjacent over the hypotenuse, and the tangent was the opposite over the adjacent. Well, notice what happens if you do sine of theta over cosine of theta. We end up getting the opposite over the hypotenuse times the, divided by the adjacent over the hypotenuse. And with fractions, we copy the first fraction, flip the second, and change that into multiplication. So notice the hypotenuses cancel, and we end up just getting opposite over adjacent. So in fact, the sine of theta over the cosine of theta in right triangle trig is just the tangent of theta. So on the unit circle, we take this to be the definition of tangent. So yeah, let's write that down. So on the unit circle, this is how we define tangent of theta. That is, tangent of theta is just sine of theta over cosine of theta. There's also 3 other trig functions that we can talk about that are given as reciprocal functions. We usually don't deal with them as much, but they do come up sometimes in identities, and we can consider the graphs and things like that. So let me just write them down for now, and then we'll finish here. So there are also 3 additional reciprocal trig functions, because they're just reciprocals of the 3 trig functions we know. So they are the secant, cosecant, and cotangent. So the secant of theta is defined to be 1 over the cosine of theta. The cosecant is abbreviated CSC of theta, and that is 1 over the sine of theta. And lastly, we have the cotangent of theta, which is 1 over the tangent of theta, And because tangent of theta is just sine over cosine, we can think about the cotangent as the cosine of theta over the sine of theta. So you can figure out values for these if you want as well, but typically they come up more in identities for problems that we're going to be looking at. Okay, so that's it for trig functions of any angle and introducing the remaining trig functions. So we'll pick up looking at some identities and graphing these things as functions next time. So this is Dr. Lennon signing off.